Yeah, fine. So last class we discussed about how to build a generating function. Okay, so we discussed few examples for the given different situations. So this example 4. Okay, so how to build a generating function we discussed. And now we'll come to the actual topic. Of course, this is also important, like what are topics we discussed. Sometimes you get a question something like this also. Build a generating function, and they give some clues to like this. Okay. now, now if you can recollect, basically we started discussing for unit 4 with the topic how you solve a recurrence relation. That is our starting point for the discussion. And why we need to solve recurrence relation also we discussed, if you can recollect. Because if you want to find the complexity of any algorithms, basically there are two steps in it. One is you just analyze the algorithm and form the recurrence relation, and the step two is once you form the recurrence relation, in the step two you solve the recurrence relation. After solving you get a value that is nothing but a complexity of the that particular algorithm. Okay, so there is a need, there is a requirement to solve a recurrence relation. So in that process we already started discussing, there are three methods. One is solving recurrence relation using substitution, that we already discussed. And second method is solving a recurrence relation using characteristic roots equation method. Am I audible?
Yes, sir.
Yeah. The third method is solving a recurrence relation using generating function. So that we discuss today in detail. Okay, so today's complete class is all about discussing or explaining or understanding how you solve a recurrence relation using a generating function method. Okay, so listen carefully. Now, if you can recollect with this, we already discussed a of x. A of x normally we call as a generating function, which is basically sigma n equal to 0 to infinity a n x power n. Okay, and this is same as if you want to write in expanded form, a of x equal to, what is the first term in this? Anyone? What is the first term in this? When you substitute n equal to 0, you get the first term, right? So what is the first term?
A naught.
A
Yeah,
naught.
it is a naught. What is the second term?
X into A1.
A1 into x power 1, or x into a1, fine. Then can you quickly
A2X
define?
square.
A2x
Yeah,
square.
a2 x square, a3 x cube, a4 x power 4, a5 x power 5. Of course it is in infinite, right? So we cannot write all, so we just written a few terms in the beginning, but because it is n0 to infinity. So this discussion we already made. Okay, now I am introducing few formulas, please understand. Okay, now see the first one. Sigma n equal to k to infinity a n x power n. So if a of x is this, or a of x is this, what will be the value of sigma n equal to k to infinity a n x power n? The value is this. So it is starting with the k term. That means n equal to 0, n equal to 1, n equal to 2, and so on, n equal to k minus 1. These terms are not there, but from the kth term I want the sum. Let us say for example k is 3, for example. Then that means I want the sum of these terms. Then what is how you write this value? I want sum of this. K is 3, for example. Then it's nothing but n equal to 3 to infinity. When I say n equal to 3 to infinity a n x power n, obviously the sum starts from here, right? Now this is equal to what? This is equal to a of x, and you deduct all these three terms. So that's what I did here. Please observe carefully, understand the formula. Okay, so a of x minus a naught minus a1x minus a2x square, so on, minus a k minus 1 x k minus 1. Why? If I want, let's say if my k is 3, that means I want the sum of the terms from here to the end. Then in that case I need to remove from a of x, I need to remove up to k minus 1 term. Okay. So therefore this formula. So suppose this formula, is it clear? Anybody any doubt? Is it clear? Anybody any doubt? Okay. Actually, I need sum from kth term to the infinity. Kth term to the infinity, how I get? It is a of x is basically starting with a 0 to infinity. So if k, just for example, I'm telling, if k equal to 3, that means I want the sum from this point onwards to the end. So in that case, this is nothing but, this value is nothing but a of x minus a naught minus a1 x power n and minus a2 x power 2. So that's what the formula here it is. Okay. Now, so you can just remember this formula. And second one is n equal to k to infinity a n minus 1, n minus 1 term x power n. In that case, the formula is it will have x into, it is same, but one more term will be reduced. There is a proof also, you need not worry about all these proofs. Just try to remember. So you understand this, right? This is a basic subtraction. And k to infinity n minus 1 x power n. Okay, so this equal to, you have x term extra, then one term will be reduced. Now next formula n equal to k to infinity, same k to infinity, a n minus 1 x power n, see n minus 2. So in that case, you will be having here x square term, then a of x minus a naught, and one term will be further reduced. Please see, here we directed up to k minus 1 term, here we are directing up to k minus 2 term. That means we are slowly reducing. Okay, then if it is n minus 3, if it is a of n minus 3, then you will be having x cube. You will be having x cube, then a of x you remove up to k minus 4. Okay, and so on and so on. N equal to k to infinity a of n minus k x power n minus 1, n minus 2, n minus 3. Now it is n minus k x power n. In that case, the formula is x power k into a of x. Okay, so these formulas will be using in the generating function method. Okay, though there seems to be little heavy formulas, but anyhow, when you start applying in the problem, you can easily understood. Okay, so you can take a snap of it for time being. Why? Because based on this, we are going to now we are going to apply these formulas for the generating function method. Okay, yeah. Now let us take a straightforward question. So solve a recurrent solution. Solve a recurrent solution. This an minus 7an minus 1 plus 10n minus 2 equal to 0. Now tell me, suppose if it is not a generating function method, let's say you are given a choice, you can apply any method. Now tell me how we do this. Suppose let's say if you want to apply characteristic roots equation method. Can you apply characteristic roots equation on this? Yes or no?
No, sir.
Why? What is the reason?
Because we are not given the initial values of the.
No. If initial values are
Okay,
not given, you
fine.
can do up to general solution.
General solution.
Okay. That means in the general solution, you will be having this C1, C2 constants. That is the only difference. Okay. But anyhow, in this problem, I think initial conditions are given. I think I mentioned the later. Yeah, initial conditions are given. Let's say these are the initial. Let me write here. A naught is how much? A naught is 10, and let's say A1 is 41. Let us say initial conditions are given. Okay. Now tell me, can you apply characteristic roots equation method? Yes or no?
Yes, sir.
Yes, sir.
Yeah. So tell me what is the answer for this? At least what is step one in characteristic roots equation method? Let me do here.
Convert to a polynomial.
Yeah. No. First you have to write a characteristic roots equation, right? You have to write what is step one. Please recollect. You have to write
T square minus 70
characteristic
plus
roots
10.
equation method. So what is the equation for this? It is t
T square
square minus 70 plus
Plus
10
10.
equal to 0.
0.
What is step 2?
Finding roots.
Finding
Find roots.
What are the roots here? What are the
2,
roots here?
5 comma minus 2.
2, 5 or 5, 2. Okay. And the third step is write the general solution. So the roots are distinct here. Okay, alpha 1 and alpha 2, the roots are distinct. So what is the general solution? What is the general solution?
n equal to
An equal to
c1 2 power n
An equal to c1 2 power n.
plus c2 5 power n.
That's all. And of course, we solve this C1, C2 using initial conditions. Okay. So, of course, Castigliane's equation method we discussed. I don't know how far you digested, but this is one of the sweet and simple method. We can easily get a solution. But anyhow, this generating function is also important on some particular situations. Okay, it has its own importance. Okay, so but at least for examination point of view, if you can't digest this, because a little more formulas are there, but at least in the background say how I am working out here. See, this is the solution should get at the end. Okay, but because either you apply Castigliane's equation method or generating function method, you should get the same answer, right? Apply any method, but the answer should be the same solution. Okay, so it is completely rough work. Okay, at the end of the booklet you do, okay, for this question the answer is c1 2 power n and c2 5 power n. It's a rough work. Okay, now let us see. So that means you have already answered with you with this, with that conference. Let's proceed. Okay, now what is, now we are coming to the solving a recurrence relation using generating function method. So the step 1 is this. So please make a note in view of examination. And normally sometimes the question will be asked like solve the recurrence relation, so and so recurrence relation using generating function method. If that is a question, you must apply this procedure only. Maybe for safe side, if you want to know the answer, you can maybe in the rough work you can apply Castigliane's equation. But you must apply this procedure. But suppose if they say solve this recurrence relation, then you have liberty to apply any method. That there is no restriction. Okay, whichever method is applicable, you can apply it. Okay. So the problem here is sometimes in the question paper they will be asking specifically a particular method like solve this using substitution, solve this using Castigliane's equation, solve this using like generating function. If that is the case, you must apply that particular method only. But if they don't specify any method, then it is fine. It's your choice. Okay. But anyhow, all recurrence relations you can't apply substitution method, only for a particular pattern you can apply. Okay, so let us quickly go through this question. So first step what we write is we write let a of x standard step. If it is a recurrence relation, you have to write these steps. One, a of x equal to sigma n equal to 0 to infinity a n x power n. This is a generating function. Okay, now what you say is multiply each term in the recurrence relation. So this is the given recurrence relation, right? Multiply each term the recurrence relation by x power n and the sum from 2 to infinity. This is 2 to infinity, and the sum from 2 to infinity. Okay, so can anybody guess why it is 2 to infinity? Why not 3 to
We
infinity?
gave condition n greater than or equal to 2.
Yeah, since you have the condition n greater than or equal to 2, or you have n minus 2 term. Suppose you have n minus 3 term also in the relation, then here the sum from dash to infinity. If you have n minus 3 term in the recurrence relation, that means n greater than or equal to 3, then sum from dash to infinity, that is 3 to infinity. If you have n minus 4 term in the given recurrence relation here, let's say n minus 1 is there, n minus 2 is there, n minus 3, n minus 4 is also there. Then in that case, it is each term you multiply with x power n only, but the sum starts with from
4 to infinity.
Okay, so that is the only difference. Otherwise, it's not fixed. Okay, why 2 to infinity? Because we have n minus 2 term or n is greater than or equal to 2. Okay, so if you multiply each term, so how many terms are there by the way in the given recurrence relation? 1, 2, 3, right? There are 3 terms. So you multiply each term with x power n, and the sigma sum is 2 to infinity. Hope you are understanding this. So n equal to this is not k, n equal to 2 to infinity a n x power n minus 7 into, so I have a n minus 1. N equal to 2 to infinity only, a n minus 1 and x power n. Please see, n equal to 2 to infinity, x power n is common. N equal to 2 to infinity, x power n is common. N equal to 2 to infinity, x power n is common. And the remaining part is from the given reconciliation. Hope you are understanding. So what we are doing is step 2, each term we are multiplying with x power n, and the sum is running from 2 to infinity. And y2, y0, 3, that we already discussed, right? Now we substitute these values. Now tell me what is this value? N equal to 2 to infinity a n x power n. What is value? It is nothing but a of x minus a naught minus a1x. Is this clear? Why? Please refer your formulas. When n equal to k to infinity a n x power n, it is ax minus up to k minus 1 term we just deduct. Okay, so as per this formula, so n equal to 2 to infinity means up to n value is 1, you have to deduct. Okay, so n value k value equal to 1 means it is a1 x power 1. Okay, so it is ax minus a naught minus 7. It's very simple. See, when n equal when you have n greater than or equal to 2 or n minus 2 term is the maximum term, there will be 2 initial conditions. So in that case, definitely in the expression, either you get a naught or a1 maximum. You will not get a2. When you get a2 here, if n greater than or equal to 3, then only a2 will come. Okay. So in that way, even if you don't know that formulas, you can straight away say, okay, a of x minus a naught minus a1x. Okay, so minus 7, this minus 7 is as it is, and you know n minus 1 term you will be having x. Please refer the formula. N minus 1 you will be having x, and a of x minus 1 term less when compared to this. Okay, so therefore here is 7x a of x minus a naught. So actually here 2 terms we removed, now we have to remove only 1 term, and the last time it will be simply a of x. See,
Sir, x square.
yeah, it is a x square is missing, sorry. So 10, you are right, 10 x square, I did not see this, 10 x square into a of x equal to 0. Okay, fine. Then here of course a little bit mass is here. What you have to do is simplify this. So this is completely a algebraic equation, right? Nothing great in it. Simplify such that a of x will be on one side and remaining expression will be on another side. Okay, if you want, you can, I'll give 1 minute time. If you want, you can simplify in your notebook. Take this equation. Okay, you just make a of x one side and remaining entire quantity other side. Then you get this. Okay, then you get this finally. Okay, if you want, please cross check this. Okay, then is it fine, or you want to do this, or you want me to do that? Is it fine?
Yes,
Can you do this?
Yes, sir.
Can you do this simplification? So when you do simplify, you get initially like this, a of x, when you take common, 1 minus 7x plus 10x square, and remaining terms will be in the other side. Then a of x equal to this value by this value you get. Okay, and 1 minus 7x plus 10x square, that you can write something like this. Okay, if you want to the separate product terms. Am I right? 1 minus 7x plus 10x square can be written as 1 minus 2x into 1 minus 5x. Okay, now here we need to apply the partial fractions. So this can be written as a of x can be written as C1 by 1 minus 2x plus C2 by 1 minus 5x, where of course C1 and C2 are constants. And C1, C2 will be solving with the initial conditions. Okay, now we have, I already mentioned, please see the page number 218 in your textbook. There are some set of formulas. Okay, that formulas, as per that formulas, 1 by 1 by 1, I already posted in your DMS group, all the 3 groups. Okay, there are 20 formulas in your textbook. I already posted in DMS group. I'll show you even on my screen also. 1 minus 1 by 1 minus ax. For this generating function, the sequence can be written as a power n. Okay, so let me show you that of a list of formulas. Then this is the image. Yeah, see this. Okay, 1 by a power n. Yeah, this is the third one, and this is the formula for this. Okay, see third one, this is the formula. 1 by 1 minus ax, the sequence is a power n. Okay, so we need not use all these things, but somehow if the problem is given according, you should be able to, from this generating function, you should be able to apply the sequence. So this table of generating functions is also important for this method. Okay, somehow you have to remember all this, but anyhow, largely we'll be using formula 3, formula 4, 5, 6, 7. Okay, maybe 1 to 10 maybe enough. Okay, so that is the reason I initially given this as you just apply genetic function only if they specifically asked. I apply this method using generating function. Otherwise, you just go for either characteristic roots equation method or why, because all these formulas you have to practice. Otherwise, there is no difficulty in this. Yeah. So as per that, 1 minus 1 by 1 minus 2x can be written as what? As per this,
A square.
yeah, no. 1 by 1 minus 2x can be written as what? No, it is
Yeah.
2 power, in place of a, what you have?
2.
2. So therefore, the series is 2 power n. Okay. So therefore, this can be written as C1 into 2 power n plus C2 into 5 power n. See, in fact, already we know this answer. Okay. We already did here with the simple and three steps using characteristic Rhodes equation. Same thing we will get it here. So once you got this, and of course solving constants, which is same like how you solved using characteristic Rhodes equation method. So we use the initial conditions. You substitute n equal to 0, you get one equation, and substitute n equal to 1, you will be getting another equation. Then of course you solve. Okay. So when you solve this, when I substitute n equal to 0. Okay, so this is n equal to 0 means this will be C1, this will be C2. So C1 plus C2 equal to A naught. A naught is given as 10. So therefore, this is your equation 1. Then if you substitute n equal to 1, so this becomes 2C1 and this becomes 5C2 equal to A1, and A1 is given as 41 in this problem. Okay, so this is second equation. Hope you know how to solve. So you can apply any method, and finally we got the answer as C1 as 3, C2 as 7. Okay, let me check both the equations are satisfied or not. So equation 1 is satisfied. Why? Because 3 plus 7 equal to 10. Then here 2 into 3 equal to 6, and 5 into 7. 5 into 7 is what? 35. So it's equal to 41. So fine. So C1 is 3 is correct, and for C2 is 7 is correct. So therefore, what is the final answer? It is an equal to 3 into 2 power n. Why? Because C1 value is 3 plus C2 is 7. 7 into 5 power n. Okay. Maybe if there is no space, it's looking like a 32 power n. That is therefore I strike it off. Okay. Normally this is the common mistake even students also will do. So they write 3 into 2 power n, but at the end it's looking like a 32 power n. So when evaluators are seeing normally person like me saying, so immediately the first impression it will be looking like a 32 power n. Okay, so therefore there is a chance that they may be striking off this. So therefore please be careful. Why? Because I observed many times, many times. So people will write something like this. Okay, or sometimes people write 3 into 2 power n. So these are something like looking like 3.2. Okay, so I'm just cautioning you. Please write down into very properly, either this or you write something like 3. That star normally can use, since we are computer science students, we can use this also star for the multiplication. So something like you please write down. Okay, is it fine? So this is how we solve a recurrent solution using generating function method. Any doubt in this, anybody? Any doubt? Anybody any doubt? So let me review. So step one is we say straight away let a of x equal to this. Then step 2 is each term you multiply with x power n, where sum is running from 2 to infinity. And of course after that you just substitute the formulas a n x power n 2 to infinity, and similarly n equal to 2 to infinity a n 1, like all these formulas you substitute. Then you make a of x as one side and remaining expression on the other side. And then you decompose into partial fractions. Then this generating functions, as per this, there are many formulas, but I just listed one formula here. 1 by 1 minus x can be written as a power n. Okay. So again, you can get this answer. Okay. And of course, from here onwards, solving constants, we already know, use the initial conditions. You can use the initial conditions and solve the constants. Okay. So let me give one question quickly and try this method. Similar, maybe you can take a screenshot of it. I want every one of you try sincerely in this pattern. I want everything to be written as it is, like 1 let a of x, everything. Okay, I know that many of you are not writing what I'm explaining. Okay, anyhow, I will be sending this right to you, right? So people are not writing, I understand. So therefore, at least you do one question, solve this. Okay, at least I will not give initial conditions. Solve this. Yeah, an. Let us say minus 5an minus 1 plus 6 equal to 0. 6an minus 2. Let me write it. 6 into an minus 2 equal to 0. Let us say a0 and a1. That sentence is there now. So you please try to write these sentences as it is. Okay, like express a of x as sum of familiar series. Express a of these lines. You please try to practice also. Okay, like step 5, decompose a of x. A of x is not a of x, and a of x as sum of partial fractions. Simplify, like whatever I mean, like multiply each term in the recurrent relation by x power n and sum from 2 to infinity. So these please mention, these are little important. Okay, otherwise okay, fine, whatever people are doing is good. Fine then. So let me explain quickly there are 2 more examples are there. Let me quickly glance over that. Maybe after that I can send the material to you. You can see maybe. Then I'll give this generating function. There is one more method, solving non-homogeneous sequences together. I'll give another assignment. So yeah, let's take this question, second question. So if you listen carefully. Yeah, solve this using, of course, generating function method. Step 1 is same, a of x equal to n is 0 to infinity n x power n. Then you multiply each term with n equal to infinity x power n. So here all are wrong. X power n, here x power n, here x power n, here x power n. Okay, I just given to another operator. Okay, she by mistake typed all this. So when you multiply this equation, then finally, yeah, when you substitute the first term n equal to infinity n x power n, this is the value. Then you will be having x term and one term will be less. X square term, one further term will be less, and x cube. And when you simplify, you'll get this. And by partial fractions, you'll be getting something like this. Okay, and this kind of things, please refer page number, like I have given 20 formulas. Okay, so for this, the answer will be n plus 1 into 3 power n. So this is 3 power n, this is 3 power n, and this will be n plus 1 into 3 power n. So this is formula number, formula, I'll tell you in the table, this is as per formula number 9. Formula number 9. Okay. As per formula number 9, you will get this. And you know that if you apply Castigliano's equation method, okay, you will be getting almost all the same answer. Then of course after that you can solve. If the initial conditions are given, you can solve. And the next example is solve this. It is again once again same story. A n x power n, a n minus 1 x power n, a n minus 2 x power n, n minus 3 x power n. X power n is missed in this all the terms. Then you substitute each term. This is wrong once again. What is wrong? Can anybody tell me what is the expression here?
So minus a1 minus a1.
A of x minus a naught minus a1x. Okay, and here this is fine, and this is also fine. And when you simplify this, you get this, and you get this finally. Okay, and for this n into power n, and this is n plus 1 to power n, and this is the formula. Okay, this formula n plus 2 plus n plus 1 by 2. Okay, so this you have at some place. I'll tell you the formula number. Yeah, as per formula number 15, you will be getting that. You just cross check, or let me explain. But once you substitute, you see, you may get doubt here. Actually, if you go for castic roots equation method, the roots are 2, 2, 2. Am I right? And if 2, 2, what do you write solution? Can anybody tell me? In case of castic roots equation method,
an equal to c1 2 power n,
yes,
c2 n into 2 power n,
yes,
plus c3 n square 2 power n.
right. But see, these are seems to be little different, but it is same. Please make a note. These two are same. Okay, why they are same? Because when you this is fine, c1 2 power n. Now you see this, when you expand this will be c2 into n plus c2 into 2 power n. Okay, and this will be when you expand. So when you simplify here, when you simplify this, and this can be like you will be getting some constants. Okay, and finally that all together, when you simplify the constants, you will be getting this only. Okay, just simplify. So constants, when you like c3 into 2, okay, and c3 into 1, so altogether they become another constant. So here if you observe carefully, if you analyze, these two are same. Only thing is that the constants in sub c1 you will get another constant, but when you solve, finally that's constant value is. Okay, so otherwise nothing great in this. Only thing is that you should know the basic formulas, first 4 formulas, and that a table which I already mentioned, page number 289, formulas in the textbook, and of course I have mentioned one copy to you also. So both of the formulas thoroughly, and this is the procedure. Okay, so this is all about genetic functions method. So again, I suggest every one of you, unless until this method is specified, okay, do not apply. You just apply characteristic growth equation method. Okay, that is very sweet and simple. You can easily do it. One for the characteristic growth equation, I already mentioned, you should be good in solving